Hello everyone and welcome back to Destin Learning. Binary numbers are at the heart of all of today's modern digital computers. To have a basic understanding of how computers work, you first need to understand binary numbers and how they operate. Let's go ahead and take a look at the material. Good morning/afternoon everyone. Today we're going to explore number systems, particularly binary, which forms the foundation of all computing. We'll learn why computers use binary, how different number systems relate to each other, and how information is represented at the most fundamental level in computing systems. This knowledge is essential for understanding how computers actually work beneath the user interface. Let's start with the familiar decimal system we use every day. The decimal system uses 10 digits, from 0 to 9. Each position in a number represents a power of 10. For example, in the number 425, the 5 is in the ones position, 10 to the power of 0, the 2 is in the tens position, 10 to the power of 1, and the 4 is in the hundreds position, 10 squared. So 425 equals 4 times 100 plus 2 times 10 plus 5 times 1. This system is intuitive to us because we've grown up using it, but computers operate on a different system entirely. Binary is the language of computers at their most basic level. Unlike the decimal system with 10 digits, binary has only 2, 0 and 1. These correspond to the physical states in electronic circuits, often on, or low voltage and high voltage. Each position in a binary number represents a power of 2. For example, the binary number 1011 equals 1 times 8 plus 0 times 4 plus 1 times 2 plus 1 times 1, which is 11 in decimal. Computers use binary because it's much easier to build reliable electronic systems with just 2 states rather than 10 or more. The hexadecimal system, or hex for short, uses 16 digits, 0 through 9 plus A through F, where A represents 10, B is 11, and so on up to F for 15. Hexadecimal is widely used in computing because it provides a more compact way to represent binary values. Each hex digit corresponds exactly to 4 binary digits, making conversion between the two very straightforward. For example, the binary number 1011 can be written as BA in hexadecimal, which is much more concise and easier for humans to work with. Converting between these different number systems is a fundamental skill in computing. To convert from binary to decimal, we multiply each digit by its corresponding power of 2 and add them up, as we saw earlier. Going from decimal to binary involves dividing by 2 repeatedly and tracking the remainders. The hexadecimal system serves as a convenient shorthand for binary. Since each hex digit represents exactly 4 binary digits, conversion is simply a matter of grouping binary digits in sets of 4 and converting each group to its hex equivalent. This makes hex an ideal intermediary between the binary language of computers and the decimal system we're accustomed to using. Now let's talk about how binary is organized in computing. A single binary digit is called a bit. It's the smallest unit of data. 8 bits grouped together form a byte, which can represent 256 different values, from 0 to 255. A byte is commonly used to represent a single character in text. As we need to store more information, we use larger units, kilobytes, megabytes, gigabytes, and so on. Each unit is 1024 times larger than the previous one, though we often round to 1000 for simplicity. Understanding these units is essential for discussions about computer memory, storage, and data transfer rates. Let's explore how computers represent different types of information, starting with text. The ASCII standard assigns a unique number to each character. For example, capital A is 65, capital B is 66, and so on. These numbers are stored as binary. Originally, ASCII used 7 bits, allowing for 128 different characters, which was sufficient for English text. Unicode expanded this to support characters from virtually all the world's writing systems, using more bits per character. UTF-8, a popular Unicode encoding, uses a variable number of bytes per character, making it efficient for both English text, which uses just 1 byte per character, and other scripts that require more complex encoding. Images in computers are essentially grids of colored dots called pixels. Each pixel's color is represented by a combination of red, green, and blue values. In a typical 24-bit color scheme, we allocate 8 bits, 1 byte, for each color component, allowing 256 levels per color. This creates a palette of about 16.7 million possible colors. Higher color depths, like 32-bit color, add an alpha channel for transparency. Image compression techniques like JPEG reduce file size by selectively discarding information that's less perceptible to human vision, while formats like PNG use lossless compression to preserve every detail but typically result in larger files. Audio is continuous in the real world, but computers need to represent it digitally. This is done through sampling, where the amplitude of a sound wave is measured thousands of times per second. Each sample is converted to a binary number. The quality of digital audio depends on two factors: sample rate, how often we take measurements, and bit depth, how precisely we measure each sample. CD quality audio uses a 44.1 kHz sample rate with 16-bit samples, while professional audio often uses 24-bit samples. This is why uncompressed audio files can be quite large. A stereo recording contains two separate channels of thousands of measurements per second, each stored as a multi-byte value. At their core, computers perform operations using binary logic. Simple logic gates like AND, OR, and NOT form the building blocks of all computer operations. For example, an AND gate outputs 1 only if both inputs are 1, while an OR gate outputs 1 if either input is 1. These basic operations are combined to create more complex functions like addition, subtraction, and eventually all computer processing. Even the most sophisticated software applications ultimately break down into these fundamental binary operations. This is why binary is so essential to understanding how computers function. Everything a computer does is ultimately a series of binary logic operations. In summary, we've explored the fundamental number systems used in computing. Binary is the native language of computers because electronic components can reliably represent two states. Hexadecimal serves as a convenient shorthand for binary, while decimal remains our everyday counting system. We've seen how computers use binary to represent various types of information: text through character encoding, images as grids of colored pixels, and audio as sequences of sampled measurements. All computer operations ultimately boil down to binary logic. Understanding these concepts provides insight into how computers work at their most fundamental level, beneath all the layers of software abstraction. Well, that's all for this video. If you'd like this video, please click the thumbs up button. If you'd like to see more videos like this, please consider subscribing to our channel. Thanks again, and I'll see you in another video soon. Bye for now.